Hey everybody, this is 3A, Inertia and Acceleration. So the scenario is Angela's stopped or in a stopped car at a traffic light when the light turns green and she accelerates. So first thing in part A, sketch and label vectors for velocity, acceleration, and net force on the car. This is not a free body diagram, so we don't want individual forces. So let's say this. Her velocity, now some people might say this, that the velocity is 0. If this is the instant that the light turns green, she hasn't yet started to move. Now maybe you interpret it a little bit differently and you say this is just a moment later, then her velocity would be to the right. So either way, not a big deal here, but she's clearly, the car's facing this way. So her velocity's that way. Well, she's going this way and accelerating, so that means this is also the direction of her acceleration there. And then, what is the direction of her force? Well, as it said last chapter, net force and acceleration are always in the same direction. They're vectors that point the same way, so the net force must also point towards the right. So here they ask a question, which way does Angela's body feel? And they're putting in quotation marks because it's not actually pushed, but which way does her body feel pushed? Explained in a short sentence. Well, we all know if we're sitting in this car and we start accelerating this way, that we feel like we rock back. So she feels pushed backward. Now, why is this? Nothing actually pushed her backwards. So the key here is that inertia keeps her still. And it's actually then the seat that comes up and hits her. And the seat hits her. But you can't actually tell the difference between yourself being pushed back into the seat and the seat coming forward and hitting you. So it's all the same to you. So this force feels very real, but it's not here. It's a figment of your imagination. So now in the next part, in part B here, it says, as she approaches a stop sign, she slams on the brakes. Sketch and label the vectors for velocity, acceleration, and net force. Okay, so velocity. She hits the brakes. She is still going forward at this moment. So that is the direction of her velocity. But she is going forward and slowing down, which means our acceleration is actually pointing back here to the left. And the acceleration and the net force always point in the same way, so the net force must also be back here this way. So which way does she feel pushed? She feels pushed forward. We've all been in a car like this where it's moving and then you slam on the brakes, she's going to shift this way. And again, because of her inertia. Which way is the car accelerating? Backward. And then finally here, which way is the net force? Same as the direction of acceleration, always backward as well. So what they're doing with this one is they're giving you two more familiar situations with the previous one and this one, and now they're going to switch to what is the specialty case for this new chapter here, this new unit. So here she's going around a curve and she goes around at a constant speed. Sketch and label the vectors for velocity, acceleration, and force again. So velocity, we go tangent to the way the car is moving. So at that exact moment, that is the direction of her velocity. Her acceleration, to go in a circle, as we discussed in class, she is turning always towards the center. So her acceleration here is pointing towards the center. And then that's where we get from the Greek centripetal acceleration. And then finally her force here, force and acceleration always point in the same way. So to accelerate towards the center, you must need a force towards the center, hence centripetal force. What way does Angela's body feel pushed? Because of inertia, it feels pushed outside the circle. So she feels like she is being pushed this way. Which way is the car accelerating? Towards the center. And which direction is the net force? Same as the acceleration always, towards the center.